In this module, we are going to discuss how we can perform Monte Carlo simulation for reliability analysis. In general, the Monte Carlo method works in two ways. One is that the method mimics the failure and repair history of components by using the probability distributions of the component states. And another way is that it tries to sample the states from the entire state space and get the inference from those states. After we conduct either one of these approaches, statistics are collected just like you will do in real life, and then the reliability indices are calculated using statistical inference. Corresponding to these two approaches, there are two main approaches to perform Monte Carlo simulation. One is a random sampling. It's also sometimes called the non-sequential Monte Carlo simulation. And the second is creating of this history, and this is the sequential Monte Carlo simulation. One of the things which we need for performing the Monte Carlo simulation is the random number generator. The random number generator is used for generating a sequence of random numbers. The properties of the random numbers are that each number in a sequence should have the equal probability of taking on any one of the possible values. And each number must be statistically independent of the other numbers in the sequence. To assure these things, several random number generators are available as part of the software packages. And one of the important things is that the random numbers begin to sometimes repeat after a sequence, which is called the cycle. Though the cycle of the random number generator must be long enough so that it's longer than the computation time for performing the Monte Carlo simulation, which means that the cycle should not repeat itself during the Monte Carlo simulation. The random numbers that we will use in the Monte Carlo simulation, they are from 0 to 1. And all these numbers must agree with the uniform distribution. Now, after we are able to have a set of the random numbers, now we can discuss that how we perform the random sampling. Let us first discuss the sampling of a component state. The basic idea, whether you are trying to sample a component state or a system state, is that the states should be sampled proportional to their probability. So the states which have higher probability should be sampled proportionately higher number of times, and the states which have lower probability, they should be sampled fewer number of times. Let us take the example of a component which has 5 states, and these are the probabilities of those 5 states. So if we want to sample the states of this component proportional to their probabilities, then one thing which we can do is that we can set the following rule, that if the random number falls between 0 and 0.1, then the state 1 would be sampled, because this is corresponding to the probability 0.1. If the random number falls between 0.1 and 0.3, the range here is 0.2, which is equal to the probability of the state 2, then the state 2 will be sampled, and so on. So if we have this rule, then if we draw a random number, and because each random number has the same probability of occurrence, so if the random number falls in any one of these ranges, then the corresponding state will be sampled. For example, if the random number that you draw is 0.56, then 0.56 falls in this range, so therefore state 3 will be sampled. If we follow this rule, then the states will be sampled proportional to these probabilities. In practice, it is more convenient to arrange this rule in the form of a probability distribution. If you look at the probability density function of this component that we have discussed, then if this is the state number 1, 2, 3, 4, 5, then these are the probabilities over here. Now if we convert this to the cumulative probability density function, probability distribution, then it will look like this. This will be at 1, this is equal to this one. Then for 2, this will be this plus this over here. For 3, it will be this plus this will be here. And here, of course, this will come to 1. Now if we draw a random number the same way as before, and it's 0.56, it falls here, then the state 3 will be drawn, and you can see that this is really equivalent to the same rule, because these projections like this, and like this, they are equal to the ranges specified over here. So this can be generalized to be used even for the continuous random variables, because the continuous random variables or basically when the differences become quite small. So now coming to the sampling of a system state. Now a system state is a combination of the component states, right? So if you want to sample a system state, it will be very difficult to first compute the probabilities of all the states and then arrange them into the form of a distribution function and then use this rule. An easier way when the components are independent is that you can sample the state of each component and then construct the system state. And we will show it in the next example. Let's, for example, look at a system consisting of two components, component 1 and component 2. And both components have got this cumulative probability distribution. Then you draw a random number for component 1 and draw a random number of component 2. And now you can see that according to this 0.946, 0.946 lies over here. So this is component state 5, and 0.601 that lies over here. So that's the state 3. So that means that the component 1 has state 5 and component 2 has state 3. So this way we are able to sample a system state by sampling the component states. Then again, you keep on going and draw a random number for each one of the components and have the system state from the component states. Now, supposing you have done that and you want to find out the probability of the system state in which both the components are in state number 3. So what you can do is that you can count the number of times that this state was sampled and then divide that by the total number of samples. For example, if you go over here, 3 was sampled once, twice, 3 times, and 4 times. So your small n becomes 4 and total number of samples is 14. So your probability over here is 0.286. The actual probability of this state is 0.4 times 0.4, 0.16. So this is different than this one. And that's because the sample size is not big enough. So if the sample size is increased, which means that if n is increased, then what will happen is that this number will tend to approach this number. So then the question arises that if you keep on performing the sampling, when should you stop? And this brings us to the question of the criterion for convergence. Typically, we use the coefficient of variation as the criterion for convergence. The coefficient of variation is equal to the standard deviation over mean. So after a certain number of samples, you compute the standard deviation and you compute the mean value and find out the coefficient of variation. And if the coefficient of variation is below the specified value, then you stop the simulation. This is most commonly used criterion for convergence. Now that brings us to the sequential simulation, where the sequential simulation is the simulation as a function of time. And this can be very useful, especially when the components are not independent. When the components are independent, then the non-sequential simulation works fine. But when the components are not independent, then sequential Monte Carlo simulation may be the preferred simulation. So here a history of events is created, and from there the statistical indices are inferred. For example, if you take a two-state component, then this will behave like uptime, downtime, uptime, downtime, uptime, downtime, uptime, and so on. So if we can find a method of generating uptimes and downtimes from the probability distributions, then you can construct this history, right? So how do we do that? This is similar to what we have done for the discrete state components. We basically have the cumulative probability distribution, where this is the probability of the random variable x being equal to or less than x, where x could be the the uptime, or the x could be the downtime. So now if you draw a random number between 0 and 1, and if this is your distribution of the x, then you can put the random number here and read the value of x over here. This can also be performed in the form of a mathematical equation. You have z as a random number. You equate that to the distribution function, and from here you can find x by the inverse of the distribution function. One of the most commonly used distributions is the exponential. So if the random variables like the uptime and downtime are assumed to be exponentially distributed, then the distribution will be this form. So you can equate the random number equal to this, and since 1 is a constant, you can rewrite this equation as z is equal to this value. And from here, x is log of z over rho with a minus sign, where rho could be the mean value of the uptime, the parameter of the distribution describing the uptime, or the parameter of the distribution finding out the downtime. If it is the downtime, then this will be the repair rate. If it is the uptime, then this is the failure rate. So the procedure for the sequential simulation is as follows. First, you determine the time to the next transition for each component of the system. So you have got many components, right? And let us say that all the components are in the up state in the beginning. Then you can draw a random number for each one of the components, and by using this equation over here you can find the time to failure for each one of the components. And from those times you find that what is the minimum time out of all these times. So the minimum time will decide when the next transition will happen. For example, if a component, say 5, it has the minimum time out of all the times to failure, then the component 5 will fail the first, and therefore the system will change its state by the failure of component 5. This can be illustrated with the help of a two-component example. Let us say that we have got two components, component 1 and component 2. And the failure rate of these two components are these in failures per hour. And the repair rates are 0.1 and 0.1 repairs per hour. So we start at time 0. And we try a random number for component. We assume that at time 0, both components are up. So we try a random number for component 1 and for 2, and we go back and use this equation over here, and we find that for component 1 the time to failure is 5, and for component 2 the time is this much. So component 1 fails in 5 hours and component 2 fails in 101 hours. So obviously component 1 will fail first in 5 hours. So we go to 5 hours and we set this time to 0, and this time we subtract 5 hours from 101 hours, which gives us 96 hours. So this component is down now, component 1, and this component is still up because there are still 96 hours left to its failure. So now this component is failed, so we draw a random number for this component to decide on when will this component be repaired. So with this random number and this repair rate, we use that equation and we find that this component will be repaired in 4 hours. So that means that the next state will change because of the repair of this component 5. So we go to 4 hours later, 5 plus 4, 9. So we set this to 0 and we subtract 4 from here, so that there are still 92 hours left on component 2. And this component now has gone from down state to the up state, so both components are now in the up state. So here both components are up state. This component, the repair time has been finished, and this we still have 92 hours to failure. So we try one more random number for this component, and using this and the repair rate, we find that not this one, but the failure rate, we find that this component will fail in 40 hours. So this component will fail in 40 hours. This component still has 92 hours. So we advance by 40 hours, 9 plus 40, 49. So this is set to 0. This is set to 92 minus 40, 52. So this component fails, and this component is still up. So now we draw another random number for this component, and then we decide that when will this component be repaired. So this component is repaired in 2 hours. So after 2 hours, we go to hour 51, and these 2 hours will become 0 after 2 hours, and this will be 50 hours still left. So in this state over here, both components are up again. Here we still have 50 hours. Here we have no hour left. So we draw a random number again and say that when will this component fail? So using this and the failure rate and that equation, we will find that this component will fail in 110 hours. So we advance 110 hours, 110 hours. Now this component fails 110 hours, and this component has only 50 hours. So obviously this component will fail before this component. So after 50 hours, we advance to 101 hours. We subtract 50 hours from here, we are left with 60 hours. This becomes 0, and then we draw a random number for this component now and find out that this component will be repaired in 11 hours. So this way we keep on going like this. So now you can see that you are going from 0 to 5 hours. Both components are up. From 5 to 9. So 5 to 9. This component is down, this component is up, and so on. So this is a description of the states, and these are the times of transition. So that's the way you will generate the history. Now if you are trying to perform the reliability study for the power system, then you will have to find out that whether these particular states are success states, failed states, or loss of load or no loss of load states, and from there then you will